Today, the webinar will be focusing on the heat and electric storage sustainable solutions that are being deployed in Turku and Dijon. Just a quick some points to highlight that during today's webinar, we will be recording this webinar, and at the end, this will be available on the project website and also on YouTube channel of the project. Please shoot the speaker review to have a best webinar experience. Also, you can keep your camera on during the panel session, but please keep your microphone off. And finally, the question and answers will be based on questions written in the chat. So if you have any questions, please write in the chat box. And then at the end of the presentations, I will be reading all the questions and the speakers will be replied to you. Then a quick overview of the agenda for today's event. We will have a first presentation in which Hadrien Rouchette from Dijon métropole will be presenting about sustainable energy storage in response. Then we will go to a specific presentation on heat storage solutions in Turku, and this will be presented by Willian Edrich from Sunamp. And then finally, we will have a presentation on superEMS, Dijon demonstration, energy storage for auto consumption and flexibility, and this will be done by Djawad, HAMACHE, and Nguyen. My apologies for my pronunciation. And they are from Électricité de France. And finally, we will have about 10 minutes for questions and answers and concluding the session. So, Hadrien, the floor is yours.
Thank you, Anna. So I'm the Lighthouse City Manager for Response in the city of Dijon, and I work for the municipality which is called Dijon Métropole. And as such, I will be giving you general insights about one of the integrated solutions of Response, which is about the energy storage. But I will start with a general presentation of Response before digging into these specific points. So the general goal of Response is to create the demonstrator for the future city in Europe. And regarding this, we need to create two positive energy districts, one in Dijon, one in Turku. The one in Dijon is composed of two positive energy blocks, which is a little bit distant from each other, but nevertheless both happen in the same positive energy district. We will try to find ways to make energy savings. So we implemented many of those solutions that we call the innovative elements in order to save energy, and also innovative elements to increase the local renewable energy production. And we will see in a minute that we also need to set energy storage systems in order to optimize the self-consumption of this local energy production. And then due to the use of these innovative systems, we will have to work with the citizens, both in Dijon and in Turku, in order to improve the living conditions and the understanding of those specific systems. We will monitor the impacts of these innovative elements that will help us reach our positive energy goal. And finally, due to this experimentation, we will get results that we would like to duplicate in other districts. As you can see, this project started end of year 2020 with more than 50 partners in 8 cities. And the goal is to finish it end of year 25. So most of the solutions are already up and running yet. We only have a handful remaining, and we are already monitoring the most of the solutions in order to build results to be shared with any stakeholder in Europe. Next slide, please. So this is a representation on how we can see the project. So many solutions, as you can see. This one is focused on the case of Dijon, which I know better than Turku, but nevertheless, it is the same idea in Turku and in Dijon. So many classical and innovative solutions for reducing the energy consumption on top left. Many solutions also innovative, cutting edge or less innovative for the energy production for both electricity and heat production for renewable heat and electricity. And one of the points here is that in order to have a common agreement between the production and the consumption, we need sometimes to have monitoring systems, management systems, and if needed, storage systems, which are on the bottom yet, and which will be the main subject of today. Next slide, please. As you know, the main point here is to optimize the self-consumption. So we have this storage, these production systems, which will produce at one point of the day or during more during summer than winter, or the opposite. And we have to make it so it is consistent with the consumption, which might happen in a different time. And in addition, we need to bring flexibility to the energy networks, both heat and electricity, in order to avoid having too high peaks in both high demand or very low demand, which wears out those energy networks and brings up the costs of maintenance mostly. And this is one, in order to do this, that's the main points that we have in response. It brings specific challenges for the heat and electricity networks. Let's see the next slide, please. Regarding the electricity, we will have a presentation from Djawad HAMACHE from Électricité de France, who works with us. And in this regard, we have specific case for electricity, which is we have most production during the day and more in summer rather than in winter, and the consumption is freely chosen by the consumers. So it can be in any time of the day, and it tends to happen at the end of the day. So not exactly the same time at which we have the highest electricity production with PV systems. So this creates a discrepancy between both, and we will need good energy management and storage. This will be presented later by Djawad HAMACHE. Next slide, please. For the heat, we have somewhat a common point, but the other way around. In this case, we tend, instead of having a strong production during the day, in particular when the sun is high in the sky, it is the opposite. We tend to have heat production which is as smooth as possible during the day in general, while the consumption is way higher during the times where we need heat, which is mostly during the morning and during the evening when people are back home. And we also have a very, very strong difference in heat consumption between the summer and the winter, which is less different than in the case of electricity. So this creates a very strong constraints on the heat, production and supply, for which we have strong challenges in storage and energy management for the heat systems. Next slide, please. Sorry, can we go back, please, just for 1 second? I forgot to mention that Willian Edrich will give us a specific presentation on this heat storage system for Turku, as they are one of the partners dedicated to this very specific challenging case. And we can go to the next slide. I'm sorry, I forgot. And this is one way we see it in Dijon. So these are examples of buildings which are implemented in the Fontaine-Douche district, and for which we have storage systems which during the day are supposed to store the energy, and during the night or the evening and the morning in the next slide. Next slide, please. Yes, here, oh, sorry, these systems, so both the batteries in light blue and the heat storage systems in darker blue shall then share the stored energy to the overall buildings. So this is a schematic which makes it looks like it's pretty simple to organize, but in fact it comes with specific challenges, which I'd like to show in the next slide. Because first you have to integrate those systems in an already existing framework of systems of energy network, but also energy production system and energy consumption system. So we need storage systems applicable to an existing network. Then those systems have to be economically performing. So this is something that was not the first main goal of Response, but Response will provide results regarding this. First, we try to optimize the self-consumption of energy, and now we will work on improving the performance of the cost of those systems. And the last one, which is a major concern, is that we need to know the best moment at which to store energy, and the best way at which to unload it from the storage systems to the consuming facilities. And this needs an energy management systems which can be pretty sophisticated for both electricity and for heat, and which relies on gathering data and the proper intelligence in order to be able to provide the energy at the best moment possible. And this will be better discussed by Djawad from EDF and Willian Edrich from Sunamp in a minute. Thank you.
Thank you so much, Hadrien. So let's move to the next presentation. Over to you, William.
Thank you very much, Anna. So welcome, everybody. My name's Willian Edrich. I work for a company in Sunamp. We're an original equipment manufacturer based in Edinburgh. I head up the global business unit for commercial industrial products. And effectively the project in Turku is one of those projects that I effectively help run. So the aim of the innovative element within the response project for us, for Sunamp, was effectively around the design iterations that we needed to go through. Obviously the final installation that we actually wanted to actually carry out. And effectively another innovative element was effectively around the business model that we would do. And I'll explain those three as we go through the presentation. You can move on. So this is an orientation slide. Some people might not have been to Turku. It's a very beautiful city. I do like visiting it. And this is effectively a wonderful building that they built for their students as part of the student foundation. There's about 5,000 apartments in this area, but they built this beautiful building here. And on the right-hand side down below, you can see there's a shipping container. That used to be the position for the heat substation between the strategic network that came from the city of Turku and effectively the 5,000 apartments that are effectively on the student village. And so what happened was that we effectively took away the existing substation, which was old and and it would be renovated as they built the new building. And effectively, that's where we effectively sited our thermal storage batteries. So if you could move on, next one. So the aim of the project, from our perspective for Sunamp, was to look at whether we could actually develop a business model for arbitraging heat between high cost of heat generation and low cost of heat generation, and whether that would be beneficial for effectively for the end client. We know across the globe, but especially also in Europe, that the development of heat networks and cooling networks are going to be absolutely critical. And we know that thermal storage effectively on those can make those networks and the interaction between the thermal networks and electrical networks work better and more efficiently as we move to a low carbon system. So we wanted to see whether we could actually develop a business model that we could roll out not only in Europe, but also across the globe. So if you could actually move on. Next slide. So design implications. So when we actually put the application in, we thought that we would have a stratification approach of using our phase change material. Our phase change material typically stores a lot of energy in the latent heat part of changing phase between liquid and solid. And we thought that we might be able to use a stratification approach using a number of phase change materials changing from 43 degrees centigrade, 58 degrees centigrade, and 70 degrees centigrade. And that was our initial design application thoughts within the application process. You want to move on to the next slide? So it's just a little slide, just once again to get people orientated at the far end, which is this bit here. This is the district heating network coming from the city, and this is the local network here that effectively goes round the 5,000 apartments. If you want to move on, just to help people get an idea of what we're actually seeing. So in June 2022, we thought there was an opportunity to effectively build what would have been our first 10-foot shipping container module, where effectively the whole of the 10-foot shipping container is actually one thermal battery. You can't open it up or look inside or anything like that. And we thought that that could be then attached to effectively a heat pump. And what would happen is that the heat would flow in and charge it when the demand was low, and then when the demand was high, we would turn on effectively the heat pump and pump it out, using that as effectively a source of heat, and actually supply effectively the heat to the local network and help them balance effectively between that and their strategic connection to the city. So that was the first one. We then realized that between June 2022 and June 2023, we got some information that effectively helped try to maybe change our approach. One is that the cost of the containment vessel at that time was prohibitively high. We've actually done some work and actually got that cost down now. We actually got confirmation that the P74 material was actually good to go and was actually commercially available from our chemists. So that was really, really good. And then the final one was that we actually got indications from Finland that they had changed their heat network regulations and wouldn't allow a 30-degree return on the strategic main. So then we came up effectively with this solution where we put in a cascade of P74 and P58 and then put in a P5 material. So this changes material at 5 degrees centigrade, and we would have used that material to effectively help with the return temperature to go back to the strategic main at the plate heat exchanger at 30 degrees centigrade by effectively switching on effectively this small chiller and reversible heat pump here that actually help balance the return flow back to the strategic main. Ultimately, that didn't need to occur And so we went to the final design, which if you actually move on to the next slide, that'd be great. Effectively back to the original thought that we would have, which is effectively a cascade solution consisting of 3 P74 degree materials, that's changing phase at 74 degrees centigrade, and 2 P58 degree materials, changing phase at 58 degrees centigrade. And what we do is we obviously, when the demand is low, and we charge up the batteries, and when the demand is high, we discharge the batteries effectively into the flow of the network. So it's a very, very simple system. There's no heat pumps or any other really mechanical systems to go on, other than effectively a few pumps and a few valves. So that's effectively how it currently works. And that was installed in the back end of 2024. And we're now effectively moving to the monitoring phase. If you could actually move on. So I just wanted to run through a few ideas. This is them actually installing it in the summer, effectively putting in things like our batteries here, and effectively putting in the plate heat exchanger and connection box, which they pre-configured. If you want to move on to the next slide. And that's effectively the finished product. So you might have remembered the picture at the very beginning of the presentation, where it was just a sealed container. We've now opened up that container. You can actually see inside, and you can see that there's effectively another 2 batteries behind here, and you can see the 5th battery in here. You can see the pipe where it's coming in from, effectively the strategic network, and effectively the pipes going out to the local network and the 5,000. We want to connect maybe on to the next slide. And there we are.
Thank you so much, William. Just want to remind you that if you want to ask any question, please do write it on the chat box, and we will answer at the end. So now moving to the next presentation, Djawad, the floor is yours.
Yeah, thank you, Anna. I am Djawad HAMACHE from EDF R&D, Paris-Saclay. I am with my co-worker Benoit and Nguyen from the same entities.
Yeah, we are in the same.
Okay, thank you. I will present our solution, superEMS, to manage storage system for a response demonstrator. The storage system, which consists on storing energy surplus and using it when it's most needed. The aims of the innovative solution are to maximize self-consumption in 2 levels, the individual level and a collective level. For our use case in Dijon city, and optimizing energy flows and reduce grid stress. Now with rising energy prices and the competitive cost of production and storing electrical energy, many cities and even individuals are deploying the system to reduce their energy cost. However, the development of this type of electricity production bring both advantage and disadvantages to electrical grid system. Advantage include increase the flexibility and reduce the cost for the cities and for individuals. While at the disadvantages include a high voltage constraint at medium level and medium level of the grid. Therefore, it's very important to develop a solution to manage and optimize the integration of this type of the system. For Dijon demonstrator, we have 2 types of energy storage system, electrical and thermal. For the electrical energy, it's in the Dijon school area, and we have a system storage system with a battery. And for the Orphitis area, you have a heat storage system to providing a flexibility. Next slide. For the storage, for the battery system or electricity storage system, it's a second life battery storage. It's cars battery, and it's a stationary energy solution. Offer an innovative answer to solve the issue of intermittency of PV production in our use case, to store the excess of electricity produced by in the day, and using this energy when we have a consumption peak or in the night. Initially, we planned to evaluate three technologies of battery: zinc air battery, LFP, lithium ferrophosphate, and NMC, nickel manganese cobalt. However, due to the difficulties encountered by the initial suppliers and partners of the project, the company, the Syria company, ultimately provided the entire storage capacity using NMC technologies. Next slide, please. Yeah. This is the battery station as supplied by Syria company and installed and commissioned at Dijon school. It's contain 7 rack battery with 80 kilowatt hour by rack, and 7 inverter DC AC to convert the energy from direct continue to alternative direct current to alternative current. And for the inverter, DC AC inverter, it's for 20 kilowatt for each inverter. The system is installed and it's commissioned in October 2024. Now we started to manage the system, the storage system, to store the energy in the day and use this energy in the night with a simple algorithm. And the objective of this storage system is to optimize the self-consumption for Dijon school area, and it's in the individual level self-consumption. And the second level is collective self-consumption. We can transfer directly the energy we pass by the grid to other area of Dijon city, like the Anjou school and the sportive complex. We have two levels of self-consumption optimization: local in Dijon school and collective with city, Dijon city. The next. Another flexibility element, storage flexibility element, it's V2G charger station at Dijon. In the response demonstrator, we installed and commissioned 6 charger stations, 5 at Dijon and Grand Dijon Habitat. It's a social housing building, and it's in this area. And the last one, it's in the mall at the same district fontaine douche. This station chargers that will help to increase the flexibility of the local electricity system by using onboard batteries to absorb or to reinject the electricity. It's requires specific embedded software as well an operating platform currently developed by another EDF entity. It's DRIV, and we integrate the management of this virtual or this onboard battery to providing of flexibility and using it like a battery to store and to absorb and to reject the electricity. The next another storage element, it's thermal storage battery. It's hot water tank at its phase with the technology phase change material PCM. It's installed and commissioned at Orvitis area. It's a social housing building, and the objective of this storage system is to stock the excess PV production in the summer, and as a preheating device to produce hot domestic water. We have two modes. It's integrated in the superEMS management. We'll integrate this in this year, and we have two modes to control the hot the storage heat storage element. We have summer mode. In the next slide, in the summer mode. Yeah, in the summer mode, it's a superEMS controlled. We convert the excess PV production to thermal energy, and in the winter it's self-controlled. It's the system is self-controlled, and it's not controlled by the superEMS. It's unused domestic hot water to kept hot by looping back to the heating substation. And this is a picture. This is a picture we can show the PV installed in the rooftop of the building, and the system of heat storage with PCM technologies. The next slide. Okay, I will continue. This is the superEMS simplified architecture, and it's divided by it's composed by multiple blocks. The first one, it's with our it's the block deployed in cloud AWS, our partner, and we started to deploy algorithm for the management of the multiple asset of the Dijon demonstrator, and ensure the cybersecurity management of all the system and administration. And for the superEMS, we for the prediction to predict the consumption and the prediction to consumption of all building and the production prevision. We get the data from multiple platforms like system information ACCADF to get the data, the historic data of consumption, and from Datanomia the production data, and the weather data for Météo France. We used all this data to predict, to estimate the future consumption and PV production. And with this, we use the Clivery tool. It's a solution developed by EDF R&D for optimizing and consumption and production prevision. With this prevision, we compute the set point to control the battery system and the heat water system and the charger station V2G deployed at GDH and at GDH. Now we started to manage with the sample algorithm for the battery installed and commissioned at Dijon school with the sample algorithm, and we will continue this year to adapt Clivery tool to manage the hot water tank and the station and the charger station. The next slide. The superEMS main element, it's Genesis. It's a multiple protocol gateway, and we use it's a remote control and centralized data collection, secure end-to-end data exchange. And with these tools, we can interface with multiple assets or information system with different protocol. And we can interface with the battery system with Modbus TCP IP protocol. We can interface with the Drive platform to manage charger station with HTTP or HTTPS protocol. We use Genesis to interface with the thermal storage system with Modbus TCP IP protocol. It's we use this solution developed by EDF R&D. Clivery, it's optimizing planning software for production system. It's developed by the EDF R&D. We adapt this tool for our use cases at Dijon demonstrator to maximize utilization of the system production and cost optimization, and we use for the prediction of consumption and the production for the best optimization of individual self-consumption in the first level, and the second level, it's a collective consumption. Next slide. This is a Genesis tool. It's a multiple protocol gateway. We can use multiple protocol like Modbus, DMP3, UC 104, or the protocol. It's conform to the standard UC 6180 50 format, and we use this for other project with the EDF R&D, and we guaranteed the interoperability between different equipment and easy interfacing with all equipment. Next slide. This is Clivery's planning software for production system, and for our use case, we will we started to we deployed a small party to manage just the storage system. It's like first version, and we will continue this year to manage all the system of response demonstrator at Dijon city, and it's based on historic data. We use the historic data conception and production and weather prevision to compute the prevision of consumption, the prevision of the production, and compute the set point for charging or discharging the system, electrical system storage, the battery at equal Dijon, and to convert the excess PV energy to thermal energy at Orvitis area. And we optimize the self-consumption using multiple. We take multiple constraints like the cost, the production, and the consumption. So orchestration of the software ecosystem. All the software is deployed on AWS cloud partner. It's a cloud partner of EDF R&D. We deploy with this interaction of all the system. Yeah, it's the internal architecture of the superEMS. We have a local database to store all information and data, and the data it's provided by information system Datanuya for the production data, Deriv for the data of charger station, and S and SC ACCEDF are for consumption data, building consumption data, and we give this data to Clevery tools to compute the prevision of production, consumption, and the planning or the set point to manage the assets. In our case, storage the battery at equal before, and the thermal battery at Orvitis. Yeah, it's the last one. Thank you.
Yes, thank you so much. We finish a little bit early than the plan, so we still have some time for questions now. I don't see any questions on the chat. Actually, there is one. So in the buildings in Dijon, on average, how much of the total electricity consumptions is covered by self-consumption? I think this question should be, yeah.
Thank you for the question. I will give some numbers here. So we have a total production of the district, which is 2,000 kilowatt peak. So around 2 megawatt peak. So, sorry, and the goal is to provide electricity to 10 residential buildings, 2 schools, and 1 sports center. So 3 schools and 1 sports center. Sorry. And I don't have an overall number. I know that at the scale of the residential buildings, it's pretty much 30% of electricity needs that will be covered by the local self-consumption. And pretty much virtually 100% of the electricity production, a little bit less, but between 90 and 100% of electricity production in the residential buildings shall be consumed directly in the district. For the city-owned buildings, I don't have the number of what share of the consumption will be covered by the electricity production, but it should be more than 30% because the power, the implemented power for the city-owned buildings is even more than for the residential buildings. And one thing is that among the 3 main sites which will be producing self-consumed electricity for the city-owned assets, those will be 3 sites producing electricity. And there will be those 3 sites consuming their own produced electricity, and the electricity they do not directly produce can be stored on site, like for the Dijon school, and they can also be shared locally with 21 other city-owned buildings, such as the swimming pool, for example, which is next to the PEB, in order to virtually keep as much electricity, as much locally produced electricity on site. So in the sites or the local sites, which are less than 1 kilometer away from the producing sites. I will check to find the number for the city-owned assets. I need a few minutes to compute that. That's a good question. Thank you.
We have one more question. And what percentage of households participate in the self-consumption?
We are still working on hiring the citizens, the tenants who will be participating. So we have pretty much 1,000 tenants total, and we started the first operation to identify them through public meetings, and this has not revealed very effective because for many reasons people cannot join. So we have only now 10% of the households which are applying for the self-consumption operation, but we are about to start a second operation for which we will go door to door in order to hire the citizens to obtain the agreement from the tenants in order to join the operation. So we aim at having around 75% of the tenants joining in the operation, and we think that we will achieve this through door-to-door campaign. So this will allow us to obtain this 75% goal. Nevertheless, even if we do not reach this goal, the business model for the investors who are, in this case, the social housing companies, will remain, will float anyway, because they will be able to get their money from other sources of income in the scope of this self-consumption operation.
Thank you. We have one more question. What innovative solutions will you implement this year in the neighborhood of Fontaine-Douche?
So again, it's a question for Dijon. So Fontaine-Douche is the district in which we have the response project progressing in Dijon. So the innovative elements that we will implement this year, so you mean year 25, I guess, so the ones which remain to be implemented now. So we we just implemented the batteries which have been discussed by Mr. HAMACHE. So those have been implemented end of last year and are set up in operation end of last year and beginning of this year. Then we are just about to start the operation of the Kier parking, which is the largest PV production system in Fontaine-Douche. So it is a large PV system over the Kier parking, and the main system that will be started this beginning of the year is the self-consumption operation with the tenants, the one I was just discussing. Yet the PV systems have been installed and are starting operation, but we still have a very important step to go regarding the innovative element is the one dedicated to the self-consumption operation for tenants. We already have the one for the city-owned assets. This one works since year 2022, and we will start the one with the tenants probably in March, so in 2 months from now. That's why we are in the process of obtaining the agreements from the tenants of each building of the 2 housing companies that we have as partners in the Response project. So those are the main ones, and but the PV systems on the roofs of those buildings are already implemented yet. If you come visit the district, you will already see those systems on the roofs.
Thank you. We have now a question to William. In terms of business model or ROI of the solutions, how profitable is it for building owners, for example of other cities? William, you're muted.
Sorry, I was turning the audio off. So with Turku, it's a bit difficult for us to answer that question directly, but I can give you an example of a different part of the world where effectively arbitration and balancing effectively the thermal grid against the electrical grid typically will have a payback of around about 3 to 4 years. So we're doing doing a project that's in the US, in a particular part of the US that we're looking at. In a different part of Canada, where we're looking at arbitraging heat onto and doing 1 hour of time shifting of heat. Typically the payback is more or less immediately in terms of the benefits to the electricity grid for that expenditure. And so it really does depend very much on the electricity grid and how you actually interplay between the electricity grid and the thermal grids that you're effectively doing. Currently, we're looking at a few other projects, say in the UK, where we are looking to put on large amounts of thermal storage and connect it up to electric resistor boilers to actually charge up those thermal batteries to actually provide, once again, frequency response and electricity grid response, demand side. Management effectively onto the electricity grid in very tight urban areas for that. In the case of Turkey, where you're charging and discharging effectively on thermally, we think that the payback will be much, much longer because the difference between the 2 prices aren't that great. But we still think if you're looking from a long-term infrastructure perspective, then it'd certainly be worthwhile actually having that actually on, and worthwhile us as a company effectively financing that arbitrage but typically you might be in the somewhere in the region of 8 to 10 years for that. So very different, so what I'm saying is very different types of business models, depending on whether you are arbitraging heat only, or whether you're arbitraging heat against electricity. And those really need to be effectively understood. At the moment, there isn't a lot of real deep understanding that we've seen globally around the interactions between an electricity network and a thermal network. But we're starting to get into those at very deep level.